into multi-taps. We'll talk about some of the block diagrams, a standard tap versus what a drop power tap is, the RF parameters of a tap and its importance, and why there are different tap dB values in a tap. So what is a multi-tap? So a multi-tap, simply, good word, taps off the main line to subscribers. So a tap typically comes in a 2-port tap, 4-port tap, or an 8-port tap. Some people call them 2-way, 4-way, or 8-way. They come in various dB values. So you can see that that's on the label. It's a 20, 21, 23, various dB values associated with taps.
Let's talk about that one for just a second again, because sure. You know, in today's networks, a 23 tap is what we would consider, you know, a high value tap.
Right.
But 20 years ago, in systems that were one-way only and didn't have any return loss considerations or return upstream path loss considerations, we used to see tap values a lot higher than that, didn't we? I remember seeing
29 to 32. I think we even designed a 35 value tap as well. So, but you know, those are the highest. Occasionally, we may see a 26, but that's very rare. 23 is typically the highest tap value we typically see.
And that is due to the upstream path loss that's also considered in the taps. And right. On the one-way only system where your upstream transmit level was not a consideration, high value taps of 29 and 32 were not uncommon. But right. Over the years, that number continues to go down.
Correct.
All right, thanks, Neil.
Yep. We're going to go through a block diagram of a tap. So first, what main components of tap? These are the tap ports, F ports. That goes down to the drop. Taps can be installed from the input port on the left, the output port, in aerial installation. So your hardline connectors go in from the left and the right. You can also install a tap in pedestal installation, where the hardline comes in through the bottom and out through the bottom in a pedestal. You would remove these hex port plugs and you put them on the other side, but connectors we can go in and out. So this left side would be the in, right side would be out, and the arrow is the direction of the main path going from upstream to the downstream, from the head end to the home, down the network.
Now, the truth is you can install these in any configuration. And we've seen them in like multi-dwelling units, MDUs, apartment buildings, where either port on either the left or right can be used. And the beauty of these is they're configurable relatively easily to use either port.
Yeah, so you can do a right angle situation. You have an input through here and an output down to the bottom, and depending on how you would like that to be installed. So both of these ports are considered the input port. Both of these ports are considered the output port. You use one or the other.
Perfect.
So this is a block diagram here. You have the input. You have, and this is what we mentioned last time, where we have a directional coupler, combination device, and a splitter. And in this directional coupler, the main signal goes in and out through the lower loss port on the directional coupler. And the tap port determines a dB value. This determines the loss going down to the splitter that splits it to this 2-port in this example. And AC is also shown as from in to out, but it does not go down the drop port in a standard video tap. So this is a directional coupler that's here, and the in and output port is unequal power divider inside the tap. Lower loss port goes to the output, has more signal level, and you tap off, or the down leg, some people call it down leg, a coupled port, tap port, has higher loss and less signal level out the tap port. Then the splitter obviously just splits that into 2 equal signals for each F port going down to each individual subscriber. And that's an equal power divider. So a 2-port tap, simple block diagram for a 2-port tap, but as you go to a 4-port tap, is just adding an extra set of two-way splitters to create a 4-port tap. Note that you have an extra 4 dB of loss going down here. So each set of splitters is 4 dB, so there's 8 dB of splitter loss going down this tap port. So you would need to select the correct directional coupler value to get the right tap value as you go from a 2, 4, and 8-port tap as well. So in this 20 dB tap, you would need a 12 dB directional coupler because you have 8 dB of loss through the splitters. So if you want 20 dB from here, 8 dB is lost through the splitters. You'll need another 12 dB through the directional coupler. So this tap has a 12 dB directional coupler to make a 20 dB tap. So an 8-way, similarly, has an extra set of splitters. So a 20 dB tap and a 2, 4, and 8-way all have different directional coupler values because of the amount of loss is split on each of the ports.
So I think when we talked about the through loss, right, of a tap, or the insertion loss of a tap, that's largely determined by the value of the directional coupler, right?
Right.
And so it's important to note that if you change a tap, you need to change it like for like on the faceplate value, or consult your design department before exchanging a 23 tap and putting in a 17 tap, right?
Correct.
Because the amount of insertion loss is actually different, and there are certain tap values where the insertion loss is all of the signal because they don't actually pass power. We would call those terminating taps, where they don't actually have a directional coupler in them.
Right.
They divert all of the signal to the tap ports. So there is a possibility in this instance, if this were a 20 dB tap, and let's say that the tap itself was broken or damaged, but the only thing that you had was, let's say, maybe an 11 tap. If you were to put an 11 value tap in a 20 value tap's place, the insertion loss is going to be different, and that'll have consequences for the subscribers farther down the line.
Correct. Because you can't create power, it's split. A certain percentage of the power goes out here. So if you have more loss or less loss going down the tap port, you're really affecting your insertion loss. So the higher the tap value, the lower the insertion loss. So higher tap value means more loss through here, but it's lower insertion loss. So if you're changing a tap, you do want to make sure you change to the same value tap. But even going from a 2-port to a 4-port tap in the same dB value, we'll have slightly different insertion losses as well, because a 4-port tap has 2 sets of splitters here, and a 2-port tap has 1 set of splitters here. So this directional coupler value is different in the same 20 dB tap on a 2-port tap versus a 4-port tap. So make sure you check the print and use the correct value tap that you need for your design.
Awesome. So these are combination devices. They have a directional coupler and a splitter or a series of splitters. And that directional coupler is what determines the insertion loss from the in to the out. And then the sum of the loss through the directional coupler and the series of splitters is what determines the loss from the in to the tap port. So back to the scenario where if you couldn't read the faceplate value, you could measure the input off the seizure screw assembly and the signal coming out of the F ports and determine which tap value it is.
Correct. Very good. This one is a drop power tap, and a drop power tap has has one or more F ports that has the capability of providing AC down the drop. And as we mentioned before, this is to power access points, could be Wi-Fi access points, CBRS radios. This is a drop power tap, and this is activated with a fuse as well. It's a little shunt that would put AC and go down one or more of the ports. And this is a typical R drop power tap. It has a little compartment here. You can open it up and you put little fuse inside here for port 1 or port 2 to turn on or turn off the power on each of the ports.
And again, those are, I think, also becoming more prevalent as more and more devices get connected to HFC networks for backhaul, like cellular radio heads, Wi-Fi access points, other over-the-air communication devices that use HFC networks for backhaul.
Right. So we're going to talk a little bit about the multi-tap RF parameters. These are the main RF parameters that are part of a tap, and we'll go through each of them individually. The first one's insertion loss, and it's measured from in to out. And the goal is to have a lower insertion loss. This is the loss that is inside this component. So the less loss is better. Lower insertion loss means longer cascades. The frequency response of the cascade depends on good frequency response on each individual tap. So these things are cascaded in multiple taps together. So the overall cascade response depends on each individual one, and it's added together. So this is a very important parameter to meet your length of a cascade. The next parameter is the return loss, and input return loss. So the input return loss is measuring from the input and the reflection of the input. You want a high input return loss. High input return loss means less reflection, more transmitted signal. This parameter is particularly important in full duplex DOCSIS FDX applications to minimize reflections or echoes, particularly on taps that are closest to the amplifier node, because the signal level is higher there. The signal level is higher there, any reflection coming back would be higher. So you want a very good return loss on taps for the input return loss. Same thing for output return loss. It's the reflection at the output. You also want a high output return loss. There's this tap loss. That's the loss going from in to the tap port. And the tap loss is actually the dB value. And as mentioned in the previous slide, it's the accumulation, the addition of the directional coupler coupled value and all the splitter losses that determines the tap loss. So in this case, if it's a 23 dB tap, it is a total loss between the input to each of the tap ports is 23 dB. And this needs to be the correct. There's an isolation from output to tap port. This is the upstream signal that should flow from out to in. But we do not want upstream signals going from the output port to any of the tap ports. So this measurement wants to make this as high as possible, the isolation as high as possible to isolate the output from the tap port. So most of the signal goes to the input. So this prevents upstream to affect a home down this drop.
It's also the reason, if we go back and imagine the combination device and how the tap is built, right?
Mm-hmm.
On the return input, that signal is going into the through leg of the directional coupler, right? With the intent of passing through that tap upstream back towards the head end. So it's very, very difficult for a technician to hook a meter up to an F port of a tap and look at the noise or the return ingress that is coming from further downstream upstream because of that port-to-port isolation in the directional coupler. So if you've ever tried to use a tap port to measure return noise that's on the system, you'll find that it's not very successful. And that's the reason why is these devices are designed and built to have good isolation between the return output test point and the RF tap port. So that's very important. I know technicians have tried to measure return noise out of tap ports. It's not successful on purpose.
Correct. And to measure those return noise, you probably best to use a probe at the adjacent output port here to measure that type of upstream noise.
That's right. And it's important to use an impedance match test probe, something that's nominally 75 ohms, so you don't create reflections by inserting the probe into that seizure mechanism.
Next parameter is the isolation from tap to tap. So obviously when you have one home connected to one of the tap ports and another home connected to the other tap ports, you want them to be isolated. So any upstream signals going from one home do not go down to affect your adjacent home. So you do want high isolation between all the tap ports.
So this is typically what we consider port-to-port isolation, right?
Correct.
So let's say a good value for port-to-port isolation would be 25 dB, somewhere in there.
Yes, correct.
So what that means is if there was 20 dB of noise that were being fed from a premise back towards the tap, that the tap itself would inhibit about 25 dB worth of energy from that port and prevent it from being transmitted back to the other port. So it's a way of protecting premises from each other, quite frankly. Now, unfortunately, that doesn't prevent that noise from being funneled back through the splitters or combiners or directional couplers into the upstream path, but it would be less impactful to the other customers on the tap.
Correct.
That's one I think we could spend a lot of time talking about, Neil, is isolation.
Yep. Isolation, correct. And we'll talk a little bit about that when we talk about conditioning as well, because the isolation between port to ports for ingress has a big impact. The noise and ingress from the home goes upstream, and we can talk about conditioning later on about that isolation. The last parameter is tap return loss. It's the same. You want a good high return loss. So